Hi everybody, I'm Jarrell from Jarrell Education, and we're going to be working on a relative velocity problem. So as always, if this video helps you and you like it, please like and subscribe to the channel. It really helps. Thanks, here we go. Alright, so let me read this problem here. So the problem has several parts to it. Okay, so we're going to go through them one at a time, and let me start by reading it. So we got this. A girl wants to swim across a river to meet her coach on the other side. The river is 28 meters wide. So I know how wide the river is. It's 28 meters. And she has, and the river has a current of 4 meters per second. So I have that marked in the picture. So I know the water's moving, from left to right at 4 meters per second. The girl can swim as fast as 3 meters per second in still water. So the girl basically is going to have her velocity vector with a magnitude of 3. The vector's going to have a length of 3. She believes that she will move a distance of 28 meters to reach the other side of the river if she directs herself perpendicular to the current. Her coach believes that this is the fastest way across. Okay, so let me point out a couple of things before I even get started. Well, actually, let's look at part A. The girl tries to swim straight across the river, perpendicular to the shoreline, at 3 meters per second. On the dot below, draw her relative velocity to the shore. So let's take that. All right, we know. Now remember, these are velocity vectors. They're not distance vectors that I'm about to draw. So here's what we know. We know the girl is going to swim with a velocity of 3 meters per second. Man, I can't write today. 3 meters per second. And then we also know that the river has a velocity of 4 meters per second. Okay? So these are two velocities. They're both affecting the same person, so we're going to add them up, right? So obviously 3 plus 4 would be 7, right? So her new velocity is 7. Wrong. Okay, that's not correct. We're not adding numbers, we're adding vectors. So yes, it is true that we have to add these vectors up, but no, it's not true that they add like numbers. Okay, so adding them vectorially, we take this one and put it on that one, or we would take the pink one and put it on the end of the other one, and we go tail to tip, and we get that vector right there. So really what we're doing in the end is we're solving that triangle. So to figure out what her what her actual velocity, she's moving, relative from like a bird's eye view, what her actual velocity is, would be 3 squared plus 4 squared equals, let's call it v squared. And so, this is going to end up being one of those special right triangles. So this is 9 plus 16 is equal to v squared. So 25 is equal to v squared. So then we know that her velocity is 5. Now I want to point something out. It just said this. On the question it says, on the dot below, draw her relative velocity to the shore. So what's this thing going to look like from her coach standing at the shore? Well, she's going to be moving 5 meters per second in that direction. Now we figured all that out, even though the question technically didn't ask for it. All right, now is the swimmer's reasoning correct? What did she say? She believes she will move with a distance of 28 meters to reach her coach if she directs herself perpendicular to the river current. So, all right, here's what we already know. We already know that the river is 28 meters across. Let's assume she starts here and she's going to start swimming. Okay, so right now I wrote an animation and I'm going to kind of look at that. So let me go to that for a second, then we'll come back and we'll solve the rest of these problems. Okay, here we have like a visual representation of that river problem. And basically it goes like this. So there's a couple of questions on what's happening. This swimmer, which is indicated in red, can swim at a rate of 3 meters per second. So that little red arrow there is 3 long. Now keep in mind, it's not, it doesn't really go with this scale. This is a distance. The axes are distances. Okay, so it doesn't really go with that, but the vector represents a velocity that's 3 meters per second. And the blue one is the water, which is pushing this way, which is a velocity. The water has a velocity of 4 meters per second. So it would make sense that as this person swims across the river, they're going to get pushed down it at the same time. Since these are velocity vectors, the red and the blue, the purple or the pink or whatever color that is can be added vectorially to get the resultant of the two vectors. Now, the river's 28 meters wide. And remember, the swimmer can swim at a rate of 3 meters per second. So let's do this right now. And right now, the assumption is she's swimming across the river perpendicular to the current. So I'm going to run it, and here we go. You can see the time counter up there. Here we go. Okay, now this red arrow here indicated only her velocity that's moving perpendicular to the river. So they're the same length, and that was 3 and this was 28, and I stopped it roughly on time, and it took 9.33, repeating, would be the amount of time it should have taken her to get across. And that's roughly what we have here. I can't stop it perfectly. So she got to the other side, but notice she's way down here, okay? So, all right, then the question is now, like, all right, well, what if we, let me move time back and put her back there. What if we took the swimmer and said, okay, might she be able to get across the river faster in some kind of way if she swam not perpendicular to it, but maybe if she swam with the current? Like, maybe that'll get her across faster. So that would mean, like, let's do this, change it, okay? Now, what I have drawn here in the pictures, this is the way the swimmer is going to swim now at 3 meters per second. This is the water at 4 meters per second. And when you add these vectorially, you end up getting, this is her actual swim speed, right, with the river carrying her. And notice, though, this is the component for her going across the river. So this component of that red vector represents the speed with which she gets across the river. So let's run this and see how much time this takes. All right, it just jumped off the screen there, but we're already at 11.44 seconds. And if I sort of back up time, when we're here, when we're not even across the river yet, we're already at 10 seconds. So we're past 9. So that took longer, even though she's swimming with the water. Now, her speed down the river is faster, but she's not getting across it any faster. And I want you to try to think about why that might be. Try to formulate in your mind for the AP exam, why is it that even though she's swimming faster, she's not getting across the river faster? But let's see what happens if maybe she swims into the current like that. And you can see here's the component of her velocity that's getting across the river, and this, I've also drawn the component of her velocity that's opposing the water. So let's run time and see how we do. So this again took a little bit, about 11 seconds to get across. It was longer. So it's going to turn out, let me bring this back and let me set the angle to straight across. It's going to turn out that when she swims perpendicular, she's going to get across the river the fastest. Okay? Now, try to formulate a reason in your mind as to why that is, and I'll change the angle again, but notice every time she changes her angle, no matter what it is, if she's not perpendicular to the river, to the flow of the river, the component with which she's moving across the river is what gets shorter. Okay, so now that we watched that, let's sort of analyze what's actually going on here. So when she goes across the river, she's going to be moving, I'm going to put her in the middle here, she's going to be having a velocity vector of 3 meters per second. So she's going to go across that river at 3 meters per second. The problem is, as we saw before, the water is kind of pushing her with a velocity that way of 4 meters per second. And we already figured that she's going to end up moving that way with a speed of 5 meters per second. Okay, so then the question becomes, where's she going to land down at the other side of that river? And that's, so answer, let's talk about B. Is the swimmer's reasoning correct? No, she's not correct. She's not going to move 28 meters. She's actually going to end up getting directed down this way, and she's going to land down there. So this distance that she moves is actually going to be longer than 28 meters. Now, is the coach correct? Well, as you can see from what I said in the piece where I was going over the animation, yes, he is correct. This is definitely the fastest way for her to get across. And one of the reasons for, well, the reason for this is the fact that she is moving this way has nothing to do with how fast she's crossing the river. And if her velocity vector points in any other direction other than directly across, the directly across component is going to shorten, which is going to make her long. It's going to take more time for her to get across the river, even though she'd be moving faster if she pointed it some other way. Okay, so right now what we're going to try to figure out is, exactly where's the question. So, swimmer's reasoning correct? No. Is her coach's reasoning correct? Yes, for the reasons stated before. Now, calculate the distance traveled by the girl to cross the river as planned. So let's see what we have. Well, let's pretend that there is, remember, let's pretend that there is no current in the water just for a second, okay? And if you look at her vector, her velocity vector, she's moving at 3 meters per second. And we know that she's going to cross 28 meters. So if I wanted to solve just that, remember, the sideways current has nothing to do with how fast she gets across it. She's still going to move across at the same rate. So I would say V, I guess we'll call this the Y direction, and we'll call this the X direction, just so we can talk about it. Vy in this case is constant. So if I draw a velocity graph in the Y direction, where this is time, I know that her velocity is 3 meters per second. I don't know how much time it's going to take, but I know her velocity is constant, and I know that the area is 28. So this turns out to be pretty straightforward to solve because we're just really dealing with the area of a rectangle. So 3 times t would be equal to 28, which means t is going to be 28 over 3, which would be like 9.33 seconds. That's how long it's going to take her to cross. So now, let me just shrink this down. Leave it up on the screen so we can still see it. Now let's look at what happens in the sideways direction now that we know the time, okay? So she has a vector this way of 4 meters per second down the river. So if we draw a velocity graph in the X direction, her velocity is constant at 4, and the time that she's doing that for is 9.33 seconds. So to figure out what the area is, which would represent her horizontal displacement, it's going to be 4 times 9.33, which would give me 30, well, the area is 37.32. So by the time she gets across the river, okay, by the time she gets across, she's going to have moved across the river a distance of 28. And then down the river, she's going to have moved a distance of 37.32. So if we're actually looking for the distance that she traveled across the river, down the river, you know, relative from the shore, whatever you want to call it, it's found, we'll just call it capital D. So D squared is equal to 37.32 squared plus 28 squared. So that means D, I'm going to just do this in the calculator, is going to come out to be 46.66 meters. And that's how far she'll have gone down the river.